Okay, today I'm going to talk about the process of stacking. This can be a concept that is just a process you go through and you just push some buttons and get a result. But what I'm trying to do here is explain why we do it and the benefits that it brings to you. The example I'm going to use today is some shots that I've taken over the last couple of nights. This is just the red channel. You would repeat this process with the blue, green, and if you used any other filters like hydrogen alpha, you would do that too. So what I'm going to do is describe firstly what it is, why it's beneficial to us, and it's all about noise reduction. The information that we're capturing is very difficult to get. There's a lot of inherent noise. There's a lot of issues with the images themselves. So what we're trying to do is eliminate a lot of the problems in there. Let's start with understanding what we're trying to achieve. If we zoom in to this image, we can see that this is effectively just a shot of a single 5-minute shot from the camera. We can see a number of issues around here. You've got these hot pixels that are just little white dots that are randomly around there from noise on the camera. And you can see it's a pretty grainy image in general. All right. So what we want to do is try and start eliminating areas of noise that are generated by the camera hardware physically first. So the first thing we're going to do here is remove the gain or the offset, I guess. So what this is a shot taken the shortest possible duration that the camera can make. Okay, so this doesn't look like much, it just looks like a black image. But if we go and adjust the levels here, you can see there's a little bit of data in here. So we're going to stretch this data down here, try and just get all the way down, then we'll adjust the curves a little to just see what's there. Now obviously I'm not going to do anything with this and I'm just clipping it, so it doesn't really matter, but what we're trying to visualize here is why we're extracting this data. So we can see by zooming in, there's a lot of noise in this. It's not a lot in terms of in the overall well depth of of the image, but it's a baseline amount, and this has an impact on the image. So what we want to do is effectively subtract these values from the master image. So this is the image raw, right? It's just straight out of the camera. What I'm going to do now is subtract, and this is done by the Deep Sky Stacker. We're going to subtract the bias. So it's going to vary, but you're probably not going to see very much at all. So we'll just push the button and we can see that there is a small amount of variation. It's just removed a little bit of noise from there. You can't see very much, but mathematically it's been done. What we're going to do next is look at dark frames. So dark frames are the inherent noise that's in the camera from thermal and or other mechanisms that go on in the duration of the camera. So what this is an image with the shutter closed, effectively black, put the cap on the telescope, and record basically the absence of light. So anything that is showing up here is an artifact from the camera. So as you can see here, we can see some of that coming through with these hot pixels, and there's just inherent bits of little randomness in the noise, right, in there. So what we're going to do is subtract that. I mean, I could stretch this to make it more obvious what it is, but I think you get the concept. So let's go back and effectively add dark subtraction. So what we should see is a lot, if not all, of these hot pixels disappear, because it will, these things are inherent to each pixel. It's the makeup of the physical chip that how much noise is in each pixel. So what we do is I'm going to subtract that. So let's go there, and hopefully we remove a lot of that noise. Yep, so it was always the same pixel, so we've effectively subtracted that from the image. So we've gone and removed a lot of that noise. What you can't see more obviously, so these ones are very white, for example, but there's one there that looks like it could be just part of the background, but in fact, if you put it in, you can see it disappeared as a result of doing the dark. So what else have we got? We've then got the other bit of calibration is a flat. So a flat is an image that's taken with a uniform brightness across it. It's a duration that effectively, well, in my case, in this camera, I've got about 20,000 units of read that I want to show here. I think the camera is capable of, I think 65,000, I'm not sure, but the point is you want to get something uniform across the board. So what this does is effectively takes and shows any aberrations that are in the optical train. So that would be dust motes sitting on the sensor, sitting anywhere on the optical train, so on the front of the lens in this case, because this is through a refractor. Or it could be anything that's I guess an error or something that's static in the mix. In addition, in my case, I'm using a filter, so the filter itself may have a bit of dust on it, or it might not be as linear. So what we do is, as we zoom in here, it's not super obvious anywhere on here that I can see that there's anything like, particularly bad. But again, it's a mathematical problem of removing anything that is in the optical train. It's always in the same position, so we can subtract it. So what it'll do is use this to subtract from this image. So let's move this around a little, just kind of get it centered a bit more. So this is the image once we remove the flat data. So you can see there's a little bit of difference. Often this can be manifested in different cases where what you would see is vignetting around the outside edges of the scope. So you kind of got that what you would see in cinemas and stuff when people are looking through binoculars. You've got that sort of dark bit around the edges. So what we've shown here effectively is what the process of calibrating an image can do. So we're going effectively from this through to this. So the improvement might not seem to be all that dramatic, but it has made a fairly substantive difference when you look at it from that perspective. So that's with all of those done. So that's a fairly significant difference. So now what we're going to try and do is, that's just calibrating. Now what we're going to do is talk about what the benefits of multiple images is and why we take them for longer periods of time. So this is a single 5-minute exposure after calibration. So what we're trying to do is use the stacking program to effectively remove the randomness, the noise from these images. So what we're going to do is, from a single 5-minute exposure, we're effectively going to double that and make it a 10-minute exposure. So this is 2 5-minute exposures merged together. So let's just look around how fuzzy it is here and then turn that on. So you can see in the process of doing that, we've effectively smoothed out the noise. That's a doubling of the exposure time. So can remove it and add it back. You can see, particularly around these stars and stuff like this, you can see that the benefit that we've added by doing the stacking. So we've gone, that's 10 minutes. So now we'll go 4 images of 5 minutes each and show what a 20-minute exposure effectively does to it. So you can start to see already now it's a fairly significant difference from, that's a single exposure of 5 now up to 20. That's 4 times the amount of time. So that's a fairly big difference. So let's have a look at what we double it again, go to 40 minutes from 20. It's a pretty big difference still. It's not as substantial, obviously, as the beginning, and it is a diminishing return kind of thing. But you want to keep going as much as you possibly can. So this is now from 40 minutes to 80 minutes. All right. And I think where this really goes to show the difference between an uncalibrated and calibrated and stacked image. So this is 80 minutes after calibration versus a single 5-minute image with no calibration. Okay, so that kind of explains why we do it and what the process is to do that. I've documented in a previous video, but you want to go and have a look at something that, although at zoomed out like this, doesn't look particularly different from like a single exposure to that one. The difference in what you can do with these is fairly substantial. So if I started and I just wanted to work on this layer only, all right, so I'm just working on this layer. I'm going to just do some really basic stretching of this data. So I'm just going to sort of zoom out a little. So I'm just going to do my levels adjustment on here, just try and stretch out the data and see what's in there. All right, so we'll just do a couple of iterations of this, and you can see as I sort of just find the background and stretch it a bit further. What you're looking at is a fairly noisy, grainy image. If I were to do that on this image, which is the 80-minute calibrated image, and go through the same process. I didn't really keep count how many times I did that. 2 times through each. So we've done that the same amount of times as we did on the previous one. So if we go back and have a look at the difference between what I was able to do stretching a single image to get the detail out versus doing the same, 2 iterations of levels and curves on that image, you can see that it's a vastly different outcome. So that in a nutshell is what you go through to do the stacking. You would, under these circumstances now, if I would go back and just go to here, view just this one, and run one of the filters over it. Just give that a go, remove the gradient from it. So now you can see that it's a lot better to work from here than where we started with down here. So hopefully that explains why we stack. Helps you with the visualization of why we do it. And you want to go and get Deep Sky Stacker, which is a good tool for the job. Did want to cover off on one of the other items that is another reason why we do stack, is that in these 16 images that I've taken over the couple of days, there were 2 images in particular that had problems with it. You can see in this one, there is a there we go. Over here, looks like a satellite, and another one running through here, and that would normally, if you just added them together in the stack, would appear on the images. So what we want to do is remove those, and the stacking process eliminates those outliers. We're using Kappa Sigma merging. So, but we have a look here at this one. This image, where is it? This image has a plane running through it. You can tell it's a plane because it's blinking. So you can see over here, where are we? You can see the blinking lights as it's been moving along. So you want to remove those as well. Okay. Hopefully that's explained everything. Go and download Deep Sky Stacker and give it a go.